All right, ladies and gentlemen, welcome back for another round. This is Mr. Doolin. I thank you so much for tuning in. Today what we're going to do is we're going to take a look at metallic solids. So metallic solids have these positive cores floating in a sea of electrons. And the atomic structure of metals can actually be used to explain conductivity, malleability, ductility, melting points, and why metals can be easily alloyed. And so what I've got drawn on the screen here is actually just an atomic diagram of what a metal would look like if we were able to actually see the atoms themselves. And so what we see again with metallic solids and metallic bonding is we get this general release of the valence electrons so that we have this mobile sea of electrons, right? And the positive cores left behind have this non-directional bonding, and so they can be easily pushed from one place to another because the bonding environment doesn't actually change, because no matter where I push them, if I took this one in the bottom right hand corner, pushed it all the way across the top, it would still be surrounded by that sea of mobile electrons. So the bonding environment doesn't change as I push these things across. And so before we move on and start talking about the different types of metallic solids, we want to again make sure that we understand and just have lined out the properties of metals because of their atomic structure. So we'll approach the sea of electrons phenomenon first, right? The mobile electrons, and remember they are only valence electrons that are released, not total electrons, so only valence electrons. This mobile sea of electrons leads to the conductivity property. Conductivity, let me spell that correctly, right? So the conductivity of metals, and when we're talking about conductivity, it can either be electrical conductivity or it can be thermal, but both of those conductivity properties are just based on the fact that those electrons are already mobile, already free to move. Now the next property that we're going to take a look at is again the positive cores, and they are not mobile per se, but we can actually push them and work them around, and we can push them and work them around because of the fact that there's this non-directional bonding that exists, and it doesn't matter where I push them in the metallic solid, the bonding environment will still be the same. And so the two properties that we get from our non-directional bonding in these positive cores is the malleability and the ductility of the metals. All right, so the next thing that we're going to take a look at is actually the alloys of metals. And this is a very, very common technique to change the properties of my particular metals, either to make them harder, to make them more rigid, or to make them softer and more workable. We can actually mix different metals together. And so an alloy is very simply just a mixture of different metals or different elements together to change the properties of that metal, right? And we can create two different kinds of alloys. So the first one, what we can do is we can add smaller atoms in to fill the gaps between the positive cores. And so I've got the positive cores drawn on the left-hand side of the screen over here, and what this would look like if we were doing this, and by the way, this is called an right? Inter should make sense because it's between the positive cores. So this is an interstitial alloy. So an interstitial alloy, we're going to put in those small atoms to fill in the gaps. And so if we look at this diagram and we see the positive cores, we can see the gaps that I'm talking about because there's spaces there between them. Now, I do not have the electrons drawn there, and that's on purpose, right? Because what we're going to do is I'm going to use the black here to actually just draw in these smaller atoms, and what they do is they'll fill in these gaps in between the metals. Right? And what that does is it reduces the mobility of, or our ability to push these positive cores around. And so with an interstitial alloy, I'm going to go ahead and put the properties down here. What we generally tend to do is increase the density of the metal because we haven't changed the volume or the spacing of those positive cores substantially, and all we've done is just put things in between. So we've increased our mass but not our volume. The other thing that we see with our interstitial alloy is an increase in rigidity. And so what I mean by an increase in rigidity is that the metal actually becomes harder. It becomes less workable. We're not able to deform it. It's less malleable and it is less ductile. And again, that goes back to the point that using the example that I used earlier, I wouldn't be able to push this positive core around as easily because now there is obstructions in the way. These smaller atoms filling in the gaps give it a different bonding environment, doesn't allow me to push it through there. And so probably one of the most common examples that you have probably heard about of an interstitial alloy is actually stainless steel. And so what we do with stainless steel is we take an iron metal, we add carbon to it, and the carbon changes the properties of that iron metal, and it makes it more dense, and it increases the rigidity so that it doesn't deform while we're using it as a tool or a knife or whatever we're using it for. All right, and so the next type of alloy that we're actually going to take a look at is what happens when we make our mixture of our metals and we put in similarly sized positive cores, right? And so the drawing that I've got now over here, this is called a substitutional alloy, because what we're doing is we're actually putting in similarly sized positive cores, and we're talking about the ionic radius here. And so what they end up doing is they substitute themselves into this matrix of positive cores. And so notice I've got 3 different green positive cores in here, and that would represent the metal mixture, right? The difference between green and blue, those are 2 different metals. And again, what we see is we're not putting anything in between now. It's just going to substitute in the matrix because they are similarly sized. You wouldn't expect these to be able to fit in the gaps between the positive cores that were originally there. And so again, what we see here is, so the most common example, I guess, that would make sense out of this would be brass. Now, brass is a mixture of copper and zinc metal. Now, copper and zinc have 2 different hardnesses. They have different unique properties for each, and what we get with the substitutional alloy is we get somewhere in the middle between them. So again, the density doesn't change, but the hardness of the metal is going to be somewhere between pure copper and pure zinc, and by varying the percent composition there, we can actually control how far we want to get towards one of the properties or towards the other. And so the big thing to understand with substitutional alloys is we're not going to change properties significantly, that the overall property of my alloy would be somewhere between what pure copper is and what pure zinc is. So the last thing that we're going to take a look at is actually oxide layers. And so what we get with metals, when we have a pure sample of a metal, the metals tend to react with oxygens and form oxides. Now, the reaction is an oxidation reaction. You've probably heard it as rusting or tarnishing, and generally it produces some very undesirable results. And so what we try to do is we try to protect our pure metals from this oxidation process, because it degrades the integrity of the metal. It makes it weaker, less structurally sound, and we don't want our buildings and all of the structures that we build with metal to fall over, right? So we have to find a way to protect them. How do we protect a pure metal from oxygen? And so the way that it works generally is that if this sample here represents my pure metal, again, we're going to alloy it in some way, but what we're going to do is we are going to put a brand new metal on the surface of our pure metal of interest. And so in this particular case, it's still going to have positive cores here. But what generally happens is that the layer that we put up here in green is more reactive with oxygen than our original metal. And what that does, if I'm going to draw oxygen in orange, is that we get this oxygen or this oxide layer that forms at the surface, and then oxygen can no longer penetrate down into my original metal that's underneath this oxidation layer. So what this does is this oxidation layer forms a protective barrier and protects my other metal underneath from actually rusting or tarnishing. And again, one of the most common examples of this is actually stainless steel. Now, I know we mentioned stainless steel earlier as being an interstitial alloy, right? And that's what makes it hard and rigid, but the part that makes it stainless is actually we have a chromium layer, right? The green positive cores there would be your chromium, and chromium is very reactive with oxygen, and so what happens is that chromium layer reacts with oxygen, forms chromium oxides, and actually then protects the interstitial iron and carbon mixture that is underneath it. And that's why stainless steel doesn't rust. I mean, technically it rusts because the chromium is already rusted, right? But the steel underneath it does not. Another very common example of this is aluminum, and aluminum does this naturally in where that the aluminum at the surface reacts and forms an aluminum oxide layer, and then the aluminum that's underneath that oxide layer no longer reacts with oxygen because oxygen cannot penetrate down into the middle of the metal. And it's important to understand that the orange here represents our oxygen, right? And it's bonding with the metal. Notice I wouldn't see any of the oxygen, right? I guess I could draw it this way, that there is an absence of oxygen within the interior of the metal that we're trying to protect. Well, all right, ladies and gentlemen, I know that was quick and fast, but if you have any questions, I'll see you in tutorials for those. Otherwise, I will see you in class.